Greetings everybody and welcome back to another video. I just did another chair intro there because the last time I did a chair intro, the video got surprisingly more views. Maybe it was the chair, I don't know. But yeah, we're back again today. It has been quite a long while since my last video. Where have I been up to? Well, I've just had absolutely no time to film YouTube videos. I had assignments from uni and then exams. And then after exams, I had a holiday because that's what you do after exams. So basically I had no time, but we are back again here today. Hopefully for the next 2 months or so, the rest of my break, I have plenty of time to film YouTube videos. Yeah, probably gained quite a few subscribers during my time off for the past, I don't know, 3-4 months. I don't even know how long it's been. So yeah, welcome to all the new people here. You probably subscribed because of the complex analysis, and that's exactly what we're going to be doing today. We're going to be starting off these holidays with another complex analysis contour integration video for you guys. And yeah, plans for the rest of the break, I'll probably do manifolds or differential geometry, something like that. I have a series plans for that, but I haven't filmed it yet. So I need to film it so you guys can actually watch it. But yeah, we're going to start off with this integral here. This one's pretty similar to one of the integrals I've done. I've done the integral of log of x squared plus 1 divided by x squared. This is log of x to the 4 plus 1. And on that video, a viewer suggested this integral, and I had a go at it. It actually took me quite a while because I kept messing up a negative sign somewhere. So I had to do so much double checking the branch cuts and the arguments and all that. And yeah, it was just a pretty silly algebraic mistake I did. So we're going to take a look at this integral here today. It's a pretty fun one. So let's jump straight into it. We have improper integral from negative infinity to infinity of this function, this log function. So let's define a function for us to contour integrate around. And well, can't really do anything else other than defining the function f of z just to be whatever's on the integrand, but with z's instead. And right away, we notice a few things. In particular, we have z squared plus 1 in the denominator, which means we're going to have poles, in particular plus and minus I, because if you solve this quadratic equal to 0, you're going to get plus and minus I. Those are going to be simple poles as well because you can factor this into linear factors. So right away, we have poles. Where are the poles? Well, it's going to be z is equal to plus or minus I. Now, we also have to be careful because we have the logarithm as well, and we know logarithms can give us, or will give us, branch points and branch cuts. So where do the branch points occur in particular? It's going to occur where the inside, which is z to the 4 plus 1, is equal to 0. And where exactly does that happen? Well, we can just solve for that directly. It's not too tricky to do. So the branch points here, we're just going to solve as z to the 4 plus 1 is equal to 0. But maybe if you've watched my other videos where I've solved similar polynomials like this one, all you do pretty much is you just bring the 1 over to the other side, rewrite it in terms of exponential form. That's e to the I times pi. But then you want to account for all the possible solutions. So you're going to multiply this by e to the 2 times pi times I times some k, where k is an integer. But in particular, you only want it to be 0, 1, 2, or 3 in this case because we have a polynomial of order 4, so you only want 4 solutions. But this we can probably simplify a little bit if we combine the exponentials together. So this is e to the I pi and then plus 2 pi I times k. And yeah, you could factor out a pi as well, or an I times pi, so e to the I pi. And then this is 2k that remains, and then we have a plus 1. And then all we need to do from here is divide by 4 in the exponent. So this is z is equal to e to the I pi divided by 4. And then we have a 2k plus 1. And I'm actually going to define this to be something, just so I don't have to write the complex exponential all the time. I'm going to define this to be, let's call it psi of k. So psi of k. I still don't know how to pronounce this Greek letter properly. I think some people have commented and you say psi or something like that. Psi, I don't even know. And yeah, that's basically the branch point, and we can probably graph this out a little bit in the complex plane. So let's do it over here. So we have a complex plane here, something like this. And then so far we have our poles at plus and minus I. So plus and minus I, that's over here and over here. So we have negative I, then we have the positive I, and then we also got the branch points as well. Now e to the I pi for 4, 2k plus 1. If k is equal to 0, that's just e to the I pi and 4, which lives somewhere over here. So this guy would be psi of 0. And then what happens if k is equal to 1? Well, it's just a quarter rotation, so it's probably going to be somewhere here. Then you have another one here, and then over here. So these guys are all your branch points. So this is psi of 1, and then psi of 2, and then psi of 3. So these are most of the important information we've plotted out already. The only thing we need to worry about is the the branch cuts. So how do we get branch cuts now? Well, first of all, I want to rewrite the function f of z a little bit here. In particular, the log function, because this is log of a fourth order polynomial, we can split this up into the log of linear polynomials, and it just makes it a bit easier for us to define what the branch cuts would be, or the arguments. So let's do that here. First of all, we have log of z to the 4 plus 1. Now, we know exactly what the roots of this polynomial are. It's exactly psi 0 all the way up to psi 3. So what we can do is we can rewrite the inside of the log as just the product running from, let's say k is equal to 0 up to 3 of z minus psi of k, like so. Hopefully you guys agree with me on this. You could check by expanding this product out, and then you'll should be able to recover the z to the 4 plus 1. And because this is log of a product, you can bring the product outside of the logarithm by turning it into a summation. So this is equal to the sum running from k is equal to 0 to 3. We have the logarithm of just z minus psi of k. Okay. Now, this logarithm, this is just log of just some complex number, complex function, I guess. How do you take the log of complex numbers? Well, there's a formula for that. It's very simple. It's just, we still have the sum here from k is equal to 0 up to 3. What you do is you take the logarithm of the absolute value of the inside. So this is z minus psi of k. So this is the real parts here. And then you have the imaginary parts, which is plus I. And then you take the arguments of whatever's on the inside here. So this is z minus psi of k, like so. And I'm going to define this argument just like before, so I don't have to write it again a bunch of times. I'm going to define this to be, let's call it a, k of z's, because it's technically a function of z. Right? So we have the sum of these logarithms here. But what happens if you take the sum of this first guy here? Well, we have the sum of log of linear things, and you can bring that all back into this product form here. And what you should get is just the logarithm, absolute value of z to the 4 plus 1. Because z minus psi k, you're doing the product on that, and that's exactly z to the 4 plus 1. So hopefully that makes sense there. And then we have a plus I, and then we still have the sum, but we sum over the ak. So we have the sum running from k is equal to 0 to 3 of ak of z. So these are just all the arguments of the function. So we have the real parts here, and then we have the imaginary part, which is just a bunch of arguments added together. Okay, so this form is going to become particularly useful later on when we do some path integration. But now we've got to figure out what the branch cuts are going to be, because we have a bunch of these AKs over here. Where should the branch cuts be defined? So hopefully you can see that each of these AKs, the branch cuts are going to be originating from one of these branch points here. So for example, A0 of z is the arg of z minus psi 0, so it's going to be centered around here. And the way we're going to construct the branch cuts is we're going to construct them so that they're kind of running outwards from the origin. So in particular, if you have psi 0 here, well, you want your branch cut to be this 45-degree line, and then the same for all the other ones as well. It just makes it nicer to work with. So we have all these guys. So if you wanted to find the argument on, let's say, psi of 0, well, let's actually write it down over here. You can define a k of z, but this is just the argument of z minus psi k. You can define this to be on the interval. Well, let's see, psi of k, well, we want the angle, so that what's the angle of psi k? It's pi and 4, 2k plus 1, so pi and 4, and then we have 2k plus 1, and then we can just add a 2 pi to this, and that defines, well, the endpoints, the other endpoint, you added 2 pi to it. So something like this if you want to be explicit. So you can define each of these branches that way. Okay, so we got all the basic information about our function f of z figured out. Now it's time to try to construct the contour. And first of all, let's call the integral we're trying to evaluate, let's just call that I. So how do we get to I in here? Well, what exactly is I? I is just the integral of exactly this complex function here, running from negative infinity to infinity, but as with always, what we're going to do is we're just going to consider the finite interval running from negative r all the way up to positive r, like so. We're going to consider only this interval, and then we can take limits later on as r approaches infinity. There's a lot of dust falling there. I don't know if you guys can see that. So this is the interval we're interested in. And now what we want to do is we want to make some kind of contour out of this in some way. Might not be too obvious how, because you kind of want to do a semicircle over this. But the problem is if you try, you're going to run into these branch cuts over here, which is not really that great because it's discontinuous. So what's the next best thing you can do? Well, you can just take detours along these branch cuts, so you can go down like this somewhat, and then you can do a little loop around this branch point, and then same for this guy over here. You can go down and then do a little loop around here. So you go in the positive direction, which is anti-clockwise, so you're going to go along this way, and then up, and then with this path down here, you're going to go down. Let's call that path psi 1. And then you're going to go through this loop here, which we'll call gamma 1. And then we'll go back up along this path, which we'll call psi 2. And then we go along here, and then you go back down in, so we'll call that psi 3. And then we'll call this path here gamma 2, let's say. And then we come back out again, and we'll call that psi 4. And then you kind of complete the path like so. And we'll call the whole entire contour, C, as always. So yeah, real axis and imaginary axis just to make the diagram look a bit more complete. And yeah, we have the whole entire arc around, and you could label it gamma 1, gamma 2, gamma 3, but I'm just going to call it just gamma in general. Oops, I just broke the chalk in half. Okay, so this is what we have. Let's try to write a few integrals down. So what do we have at the moment? So over on this side now, what we have so far is that the contour integral over C as of f of z dz, we can decompose this into each of these separate parts. So first of all, we have the integral running from minus r all the way up to r, and then we have plus the integral. What else do we have? Integral of, well, psi 1 all the way up to psi 4, but let's just write this as a sum just so it's nicer. So we have the sum now. So we have the sum running from k is equal to 0 up to 3 of integral over psi k, and then we have the integral over gamma 0 plus the integral, or not gamma 0, gamma 1 I meant, and then plus the integral over gamma 2, and then plus the integral over big gamma here. And what we're going to do now, you guys are going to trust me for this, but the integrals of gamma 1, gamma 2, and big gamma, they're going to vanish as you make these circles really, really small, and the big arc of the contour really, really big. So these guys over here, they're just going to go to 0 in the limit. You guys are going to trust me on that, and I might give you a proof of that at the very end of the video. And what we're going to just focus on now is what's remaining. So how do you calculate the contour integral, and how do you calculate the contours, the integrals over psi k. So first of all, contour integral over c of f of z, that's not too tricky to figure out. It's just a residue theorem, because as you can see, that contour, it's enclosing the pole at I, which is a simple pole, which is nice because they're nice and simple to evaluate. So yeah, I guess residue down here. What's the residue going to be? Well, the residue is at z is equal to I of the function f of z. And how to calculate that, that's just the limit as z approaches the pole, I of z minus the pole, and then you multiply by the function, which is log of z to the 4 plus of 1. You divide it by z squared plus 1, but you know you can decompose that into difference of perfect squares. So something like this here. So z minus I, those guys will cancel, and you can just safely take the limits as z approaches I. What happens in the logarithm here? Well, we have I to the 4th power, which is 1, so this is just log of 2. So yeah, this is equal to the logarithm of 2. And then what happens on the denominator? Well, this is I plus I, which is 2I. So you divide by 2I here. So yeah, that's basically the residue. And if you want to calculate the contour integral there, you just multiply everything by 2 pi I. So the contour integral now of f of z dz, this is just equal to 2 pi I times this guy. But the 2 and the I will cancel, leaving you with pi times the logarithm of 2. Okay, so that's basically what we have for the residue, or the contour integral rather. So the contour integral, what is that going to give us? Why is this blackboard not moving? Oh dear, did I break it? There we go. So this contour integral over here, this is going to turn into just pi times the logarithm of 2. And now for the probably more interesting part of this video is how to calculate the integrals over these psi k's here. And the integral from negative r to r, this is going to approach just the I integral that we started off with in the limits as, yeah. So everything here is in the limits as r approaches infinity and epsilon approaches 0. So how to calculate the integrals over psi k? Well, the trick to doing this, it's a bit tricky, I think, to do it one at a time. It's nice to do it in these pairs here, where you pair up the paths along the branch cut. So let's try to do that on the next blackboard, and we'll see where we can get with this. Okay, so I'm just going to do the integral over psi 1 and psi 2. So I'll draw out a little picture of what's going on here. So this was our psi 0, and this was the branch cut going out like so. And then we had two paths, which we called psi 1, which went down. And then we had psi 2, which went up like so. And we want to calculate the integral over these two paths here. And the idea is these two paths are going to approach each other in the limits. We want them to squeeze into this branch cut over here. So let's try to calculate this over here. We want to calculate the integral over psi 1 and then plus the integral over psi 2. And then we want to kind of do this in the limits as they approach each other. So I'll write some funny notation. So limits as psi 1 approaches psi 2 and the other way around as well. So these two are going to kind of squeeze into each other. And now I guess just to make things a little bit more clear, we want these two to approach a path that literally runs on the branch cut. So what we really want is we want to approach a path that literally lies on the branch cut here. Don't know if you guys can see that too easily because this is green. Maybe I'll try to use orange or something. We want these two to approach a path that runs literally on the branch cut. And we'll orient it outwards just so it's easier to work with. And we'll call this orange path here, we'll call it omega 1 here. Okay, so what happens in this funny limits here? Well, the integral over psi 1, notice that it's going to basically approach the opposite of the integral over omega 1. So this is going to be equal to a negative the integral over omega 1. So this is the integral over psi 1, that's what it approaches. And then what happens with the integral over psi 2, what happens as it approaches omega 1? Well, it basically becomes omega 1. It's oriented in the correct direction, so we have a plus integral over omega 1 here. Let's just put a little cloud around this because I like those Friedrich Scholar clouds that the guy always draws in his lectures. Okay, so we have this so far, and what we're basically integrating is just the function, so we'll just plug in the function. What was the definition of the function? It was the logarithm over z squared plus 1, but I'm going to write the z squared plus 1 in the denominator first for both of these, and we'll put the logarithm in next. And remember, we had that funny form for the logarithm that we rewrote it in. It was the log of the absolute value plus I times the sum of all these arguments here. So let's rewrite it in that form. So we have the log guy. I won't bother writing out the whole thing because something nice will happen later. And then we have plus I times the sum of all those arguments, which I'll kind of list out. So this is A0 plus A1 plus A2 plus A3. Technically, we need comma z's everywhere, but that's just going to get messy. So you guys get the idea. We have the sum of all these arguments here. And I need another brackets to close off. Now, here's the important thing here. If you take psi 1 and psi 2 and you make them approach each other, notice that on either side of the branch cut, if you center yourself on this branch point over here, the arguments are going to be well, not the same. They're going to be differing by exactly 2 pi. So if you center yourself on this size 0 here and you approach from both sides, the arguments that you get for this would be a0 here. These guys would be completely different. They would be off by 2 pi. But remember, we also had those other points as well. For example, we had psi 3 down here as well, and the branch cuts for psi 3 was going down this way. So from psi 3's perspective, it doesn't matter which way you approach this branch cut over here. The arguments you get from both sides are going to be the same, right? So in particular, if you take a look at the a0s over here, for this top line, which came from psi 1, what's the angle that a0 is going to be approaching? Well, it's going to be approaching, well, we're going up this way, so that's going to be pi and 4, but we have to spin around, so that's pi and 4 plus another 2 pi. So a0, that's going to be approaching pi and 4 and then plus 2 pi. And how about down here? What's a0 going to approach down here? Well, this integral came from psi 2, and psi 2 is approaching back this way over here, but that's just going to be pi and 4. So this guy, that's going to be exactly pi and 4. And A1, A2, and A3, these are just the arguments, but you take a look from the perspective of psi 3, psi 2, and psi 1, it doesn't matter which way you approach this branch cut because it's going to give you the same value anyways. So A1, A2, A3, these are technically functions of z, but they're going to look the same on both of these integrals. Okay, so this is really quite nice here, because notice we're integrating on basically the same path, and we have an integral, a positive integral, and then we're subtracting an integral on the same path. So in particular, you can combine these two integrals together, and a bunch of things cancel because we have a log minus a log, so these guys are going to cancel. Log is continuous, this is the real log, so it's continuous on both sides of the branch cuts. And as we discussed before, the A1s will cancel because we have A1 minus A1, they're the same, and then the A2s cancel, and the A3s cancel as well. And you're basically left with pi and 4 minus pi and 4 plus 2 pi. So pi and 4 minus pi and 4 plus 2 pi. The pi and 4s are going to be gone, leaving you with exactly a negative 2 pi. And don't forget the psi here as well, that's important. So all in all, what do we get for the sum of these two integrals? This is going to be equal to the integral over omega 1. We have 1 over z squared plus 1. Okay, and then we said there was a negative 2 pi here, and then we multiply by the I. That's just a constant, so we can bring it out. So we have a negative 2 pi I, which lives at the front, and then we integrate with respect to z. And we're basically left with the integral of 1 over z squared plus 1. That's just going to become an arctangent later on, but there's quite a lot more to go from there. It's not as simple as it seems, actually. So this is the integral over omega 1. Okay, and what you can do is you can repeat the exact same thing for the integral over psi 3 and psi 4, so the sum, and what you'll get is basically the same thing. So if you take a look at the limits as psi 3 approaches psi 4 and back the other way as well, what you'll find is that this is equal to, so integral over psi 3 plus integral over psi 4, what you'll find is this is going to give you basically the same result. It's negative 2 pi I, and then you have the integral, but let's call it omega 2 this time, of 1 over z squared plus 1 dz. So omega 1, that was the path lying on the branch cut, originating from psi 0, but omega 2, that's going to be the branch cuts originating. I really should have called it omega 0, so it lines up with psi 0, but hopefully you guys get the idea. So psi 2, let's do another little, so if this is psi 1 here, then you have this branch cuts going out, then omega 2 would just be this path running directly on the branch cuts, and then you have the two psi 3 and then psi 4 here. That goes in and then back out. That's the idea. So we have these two integrals over here. So what happens if you take a look at the sum of all these psi k's here? Let's put it over here. So now if we consider the limits everywhere of the sum of the integral of psi k, going from 0 to 3, this is going to give you, well, we have negative 2 pi I, which is everywhere. I just realized my audio stopped recording for a bit there. Hopefully it wasn't too long. So it's back now again. Don't know why that happened. So we have the limit of the sum of all these integrals over psi k. So this is going to be negative 2 pi I. And then we just have the integrals. So we have an integral of omega 1 and then of 1 over z squared plus 1 dz. And then we have plus the integral of omega 2 of 1 over z squared plus 1. And then we have a dz, like so. So this is what we get if we sum all these psi k's together. And now all that's really left for us to do is evaluating these two integrals over here. That's going to be probably the most algebraically confusing part of this video because I made many algebraic mistakes when I tried this for the first few times. So yeah, once we got that, we basically got the sum of all these guys. All these integrals are 0, so we basically just need to rearrange for right. So we're actually quite close, but still quite far because of all the algebra that's left for us to do. So let's try to do that on the third blackboard now. And yeah, hopefully I do not mess up. I forgot to bring my notes today, so I really don't know if I'm going to be doing things correctly until the very end. So hopefully we do this correctly on the first go. So what we want is to evaluate the limits of the sum k equals 0 to 3 of the integral over psi k. And this was equal to negative 2 pi I integral omega 1 of 1 over z squared plus 1 dz, and then plus integral omega 2 of 1 over z squared plus 1 dz. So how on earth do we go about evaluating this? Well, first of all, these integrals, they're going to turn into some arctangents. So this guy over here, this is going to be the arctangent of z, and we need to evaluate this from the starting point of omega 1. Now omega 1, that was starting at e to the I pi on 4, so we need to evaluate from e to the I pi on 4, and then we need to go up to infinity pretty much, but we need to take the limits so we can be careful. So this is e to the I pi on 4, and then we take the limit as r approaches infinity. And this guy over here, basically the same thing. Same thing over here, but we're going to have e to the I 3 pi and 4 instead, going up to r e to the I 3 pi divided by 4. All right, now this arctangent over here, we can rewrite this in terms of a logarithm. So we can actually evaluate arctangent of complex numbers, otherwise there's not really any other way to do it. So what's the arctangent in terms of a logarithm? It's 1 divided by 2i, and then it was the logarithm of, I believe it was 1 plus I times z at the top, divided by 1 minus I times z. And here I have choose the principal branch of the logarithm. So if you want to, you should really call this capital A arctan, and you can call this capital L. I think that's a convention people usually use if you want to refer to the principal branch. The principal branch, I believe it's negative pi up to pi. But it actually doesn't matter, because the thing with logarithms, if you choose a different branch for the logarithm, you're basically just adding another 2 pi I constant or something at the ends here. And because we're doing anti-differentiation here, it doesn't matter what constants you have in the ends, because roughly speaking, when you plug in the bounds, the constants will cancel. So you can choose any branch of the log you want. I'm just going to go for the principal branch here. So basically, you'll have this expression inside both of these square brackets over here. And now we can start plugging in 4 of these numbers. So we need to evaluate this big log over here on 4 separate things. That's going to be pretty messy to do. So what I'll do, we'll kind of have to do a few steps in our head, and hopefully you guys can follow along just so we don't have to write everything down. So first of all, notice that we're going to have, well, this is negative 2 pi I times the limit as r approaches infinity. Make sure you hydrate yourself. So what do we have? Notice that we're going to plug in r e to the I pi and 4 into this, and then subtracting off e to the I pi and 4. And over here, so this is a plus here, we're going to be plugging this upper bound in and then subtracting this guy off. So what we're going to do is we're going to combine the upper bounds together. So we're going to get 1 over 2i, and notice we can factor this out as well. We can leave it out the front. So this will cancel with the 2i out over here. We're basically going to evaluate this log at this upper bound, and then adding the log evaluated at this upper bound over here. Let's worry about the upper bounds first. So this is going to give us the logarithm, and it's log plus log, so you just multiply the arguments together. So it's going to be log. Now let's plug r e to the I pi and 4 in. This is going to give us 1 plus I, r e to the I pi and 4, divided by 1 minus I, r e to the I pi divided by 4. And then multiply by, now we plug this upper bound in, so we're going to get 1 plus I r e to the I 3 pi on 4, divided by 1 minus I r e to the I 3 pi divided by 4. That is a lot of writing, so hopefully you guys agree with that so far. And now we're going to subtract off all the lower bounds together. So you're going to subtract off the logarithm evaluated at this lower bound minus the logarithm evaluated at this lower bound. We can factor out the negative, and then we get the sum of the logarithms. So now we basically repeat this exact same thing, but we have the lower bounds instead. So what is that going to give us? Well, basically the exact same thing, I believe. It's a logarithm. We have just rewrite everything here, but without the r's, I believe. So this is 1 plus I e to the I pi on 4 divided by 1 minus I e to the I pi on 4 times 1 plus I e to the I 3 pi on 4. Then we have divided by 1 minus I e to the I 3 pi on 4, like so. Okay, this is a lot of algebra to work through now, but it's not too bad. First of all, we have I times e to the I pi and 4. I is just a quarter rotation. So in fact, you can get rid of this I here, and instead of pi and 4, this is going to become a 3 pi and 4. So let's rewrite this. So this is I times 3 pi on 4. And you can do the same thing down here. You can get rid of this I and turn this pi and 4 up over here into a 3 pi divided by 4. And you can do something pretty similar here. 3 pi and 4, if you multiply by I, that's just going to rotate down to 5 pi and 4. But 5 pi and 4, that's just the opposite of pi and 4, sorry. So get rid of this I, and then this is going to turn into a negative here. And then instead of 3 pi and 4, you're just going to get pi and 4, like so. And you can do something similar down here. Flip the sign because we're going back the other way. Get rid of the I, and instead of 3 pi and 4, this is going to become just pi and 4. So hopefully that is correct there. And then you can do basically the same thing over here. So this is 3 pi and 4, but get rid of the I. Get rid of the I again, and then this is 3 pi and 4. And then here we get rid of the i's, but we flip the sign. So this is going to be a plus down here, and then we have a negative up over here. And instead of the 3 pi and 4, it turns back into pi and 4. So yeah, a lot of manipulation going all at once there, but if you're not too sure, then just write it down and work it through slowly by yourself, and hopefully you get to what we have here. Okay, and I really don't know what else to do from here other than just multiplying each of these inside of the logarithms out and seeing what you get. So first of all, the two i's cancel. Let's go down here. We have a negative pi still outside. We have the limit as r approaches infinity. We have the logarithm of, now what happens if you multiply the numerator together? You're going to get 1, and then we have 1 minus r e to the I pi and 4. Let's move this up a little bit so you guys can actually see what I'm writing. So we have minus r e to the I pi and 4. Then we do this guy over here, but this is plus r times e to the I 3 pi and 4. And then we multiply these two guys together, but this is going to be a negative. We have 2r, so this is r squared. E to the I 3 pi and 4, e to the I pi and 4, that's exactly just a e to the I times pi, which is negative 1. So this is going to flip the sign here. And all of this is going to be divided by, well, we'll do the same thing. So we have 1, then we have plus r e to the I pi and 4. And then we have the negative r e to the I 3 pi on 4. And then we have, this is negative r squared. But we have r squared, then e to the I 3 pi and 4 times e to the I pi and 4 is e to the I times pi, which is negative 1. So again, the sign flips here, and that should be it, hopefully. So close brackets. Okay, and we do the exact same thing over here. So we have negative, we have the logarithm, and I'm just going to go through this one quickly because it's basically the same thing. We have 1 and then minus e to the I pi on 4. Then we have plus e to the I 3 pi on 4, then this is going to give us negative is negative, and then a negative 1 as well, so this is plus 1 here. And then we divide this by, this is going to be a 1, and then we have a plus e to the I pi on 4, then minus e to the I 3 pi on 4, and then we have negative, positive, which is negative, but then we have the e to the I pi here, which is negative, so this is going to be a plus 1 once again, and then we have a closed bracket. So that's what happens if you expand everything out there. Now, what's the next thing we could do? We could try to take the limits now. Let's see what happens if we take the limits. So I'm going to bring everything over to this side. So now if we evaluate the limits, this is pi, okay. And now notice we have, polynomials essentially in R. Now we have an R squared polynomial over an R squared polynomial. So as R gets bigger and bigger, the contributions from all the lower order terms won't matter. You just have to take a look at the coefficients of, the leading coefficients in the numerator and denominator. It's just 1 divided by 1. So if you take the limit, well, the inside of the logarithm, that's just going to become 1. Right? But if the inside of the logarithm becomes 1, that is going to be 0. So basically all of this stuff over here, well, including the log as well, this is going to go to 0 as R approaches infinity. So we have a negative pi here. This stuff doesn't even matter anymore. And all we need to worry about is what happens over here. So I'm going to write that on the left-hand side, so we have negative pi. The nice thing is we have a negative logarithm, so we can cancel the negatives there. So no more negative. Then we have the logarithm. What's on the inside of the logarithm? Well, we're going to have a 2 plus stuff, because there's the 1 plus 1 there. What do we have? We have e to the I 3 pi and 4, and then minus e to the I pi and 4. What exactly is that? It's not too tricky to figure out, because e to the I 3 pi and 4, draw it over here probably. E to the I 3 pi and 4, you can think of a vector pointing this way. And e to the I pi and 4, that's a vector pointing up this way over here, but we want to take the negative of that vector. So the negative of the vector goes down here. And if you do vector addition, what you'll get is, well, you go up and then you go back down again. The lengths of each of these vectors are the same, so it's 1 here, and then this is a right angle triangle pretty much, because e to the I 3 pi and 4, e to the I pi and 4, it's off by an angle of 90 degrees. So you can find the length of this hypotenuse on the base on the real axis. That's exactly square root of 2. So if you do negative e to the I pi and 4, add it with e to the I 3 pi and 4, that's just going to give you negative square root of 2. So this is a negative square root of 2 here. And then you can do a similar thing with the denominator, e to the I pi and 4. Let's do it here. So e to the I pi and 4 is going up this way. Then e to the I 3 pi and 4, that's going up, well, that way there, but you take the negative of that, so you go down this way. So you do the vector addition once again. This is lengths of 1. You have the 90 degrees here. So this goes along the real axis by root 2. So it's a positive root 2 that you have in the denominator. And this is really quite nice, because now it's a real number. Well, assuming the inside is not negative, which it shouldn't be. So this is equal to now pi. I think you want to rationalize the denominator here, but I think if you go back to the start there, you have to rationalize again. I'm going to do something a bit different. Let's just do a logarithm. Now we have 2 minus root 2. I'm going to rationalize the numerator, which sounds a bit funny. So 2 minus root 2, and then we're going to multiply this guy by 2 plus root 2. 2 plus root 2, and then in the denominator it was 2 plus root 2 once again. So what is this going to give us? Well, it's just going to be pi, and then we have the logarithm of 2 times 2 is 4, and then we have, well, this is just difference of perfect squares. What am I doing? So we have the 4 here, and then you just subtract the second guy squared, which is 2, so 4 minus 2, nice and simple. And then down here, this is where you get the 4, and then root 2, you have 2 of those, so this is 2 times root 2, and then times 2, so that's going to be plus 4 root 2, and then you take root 2, that's going to be another plus 2 there. So what do you get from this? This is going to be pi. Then we have the logarithm of Oh dear, we have 2 divided by. 4 plus 2 is exactly 6 plus 4 root 2, and we can simplify this a bit further. This is going to be pi logarithm of 1 divided by 3 plus 2 root 2, and because we have the funny fraction here, you can take the reciprocal, but you put a negative outside the logarithm. So if you sum all the integrals of the psi k's together, what you get in the very end is you get a negative pi times the logarithm of just 3 plus 2 times the root 2. And that's basically the longest section of this video. I don't even know how long I've been filming for. I'm looking at the clock now, it's probably been like close to an hour. So that's what we get. Let's put things back onto the original blackboard, which is, yeah, here. So what we just found is the sum of the integrals over psi k is going to give us a negative pi logarithm of 3 plus 2 times the square root of 2. I managed to do this without using notes. Amazing. So all my algebra checked out, I believe. Okay, and we're basically done now. We just need to bring this term onto the other side. So in the end, I is equal to, we have pi times the logarithm of 2, and then plus pi times the logarithm of 3 plus 2 root 2. But we can factor out the pi and combine the logarithms together. We just have 2 times the inside of the other logarithm. So in the very end, or almost the very end, because I might want to show these integrals as well, those go to 0. So we have pi times the logarithm of 6 plus 4 square root of 2. And yeah, that is the final answer. So if that is all you came for, the final answer, then there you go. Thank you for watching, and I'll see you in the next video, I guess. But we're not quite done yet because I do want to show that these integrals go to 0 as well, just to make the video feel a bit more complete. Yeah, so that's the answer. Let's go ahead now and show that the integrals over those gammas, those go to 0. I don't think that's too tricky to show. You just need to bound the logarithm and reverse triangle inequality a bunch of times, I think, and then you're basically done. Yeah, let's use this blackboard over here. Where did the duster go? There it is. So we'll do things very, very roughly here because otherwise we'll be here for 2 hours. Let's take a look at the integral over, let's do the gamma integral first of the function f of z dz. So we estimate this guy here. Now this is going to be, first of all, this is going to turn into the integral if you parameterize using z is equal to r e to the I times theta. What you're going to get is the integral over some set a here. Now I just write a in general because the integral over gamma, you can kind of break it up into these 3 sections and you can choose a depending on which section you're on. So we'll just do some sets a in general of the logarithm of r e to the, or this is r to the 4, e to the 4 times I times theta because you raised z to the 4 plus a 1, and this is divided by, let's see, we have r to the r squared e to the 2 times I theta plus 1, and then you have the differential here, which is I times r e to the I theta d theta. So absolute value of this integral is the same as the absolute value of this integral, but it's also less than or equal to if you put absolute values inside the integrand. And it's nice because the I and the e I theta will cancel. This r will pop out to the front. So this r, you can drag it out over here. And now we just need to bound the logarithm, and we can find a bound for the denominator as well, which isn't too tricky to do. So this is less than or equal to, we have r. Now with the logarithm there, it's not too tricky to bound because log of a complex number is exactly log of the modulus of the complex number plus I times the argument. But if you take a look at this expression here, it's really simple to bound because you can just bound this argument here. So let's say this is less than or equal to log plus some constants, right? So if you take a look at the absolute value of log, this is less than or equal to the log of the absolute value plus some constants here. And the absolute value of the inside, which is right over here, you can find the maximum of that quite easily because you can just take theta to be, I don't know, 0, for instance. And then you're going to get r to the 4 plus 1, so you can use that as an upper bound. So once you have that, you can just bring that guy to the outside. So that's going to be log of r to the 4 plus 1. So hopefully this is correct. And then you have the denominator, which you want to bound as well using the reverse triangle inequality. So the way you do that, this guy, you can write this as something minus the negative of 1 here, because that's the setup you want for the reverse triangle inequality. And this guy is greater than or equal to the absolute value of the first guy, which is just r squared, minus the absolute value of the second guy, which was just 1. So you can bound the denominator below, which means you bound the reciprocal above by 1 over r squared minus 1. So you can bring that guy to the outside as well. So this is r squared minus 1, something like this. And then you're basically left with the integral. I forgot a plus c here. You're basically left with the integral over a. And this is some constant k, and it's finite, because you're going over a finite interval, and you just take the limits on that. And it's very easy to see that this guy goes to 0 because this denominator is going to outgrow this r here. The logarithm is not going to outgrow anything, really, so it's just going to go to 0. So you can argue that the integral over gamma is bounded above by 0 in the limits, so it's basically 0. And how about the integral over the little gammas? Well, I'm only going to do this for gamma 0, let's say. Or gamma, I guess gamma 1 is what I called it. I guess you'll have to write this as, the integral on, again, some set A of the logarithm of, we have something to the 4, but that's as psi 0 plus epsilon e to the I theta, and this guy raised to the 4th plus 1, and then this is divided by, this is psi 0 plus epsilon e to the I theta, raised to the 4, no, squared, and then plus 1, like so. So d, no, not d theta. We want I times epsilon, e to the I theta d theta. I believe that is the correct differential. And you can use very similar arguments to before. You can take the absolute value of everything in here. These guys are gone. You can bring the epsilon to the outside. So this is gone to the outside. And essentially, you just want to find the maximum for the inside of this logarithm over here. You can set theta to be equal to 0, for example. And that way you can have a bound of, let's say, epsilon, and then we have logarithm. If you do it properly, it's something like 1 plus epsilon raised to the 4, and then plus 1 probably, something like this, and then you have divided by, you do reverse triangle inequality on the denominator, and yeah, if you write this out, you can probably get this looking something like epsilon minus 1, something silly like that if you do reverse triangle inequality twice down there. Maybe plus a constant up here because you bound the arguments of the logarithm as well. And yeah, it just goes to 0. I just did that really roughly because I don't want to spend too much time on this. I've had enough of doing it on this channel here already. So yeah, I don't know if you guys want to see this whole process of showing the gammas go to 0, but if that's something you want to see me do properly in the next few videos, then let me know, because I just find this boring. I just can't be stopped doing it every single time. But yeah, that basically completes everything for this video. I've been going on for like an hour of recording time pretty much. So yeah, that's all for this video. Hopefully you guys enjoyed. Manifold series is coming up during the holidays. I think I mentioned that at the start of the video. So make sure you subscribe if you want to see that. But yeah, thank you all for watching, and up until the next one, have a wonderful day, and I'll see everyone later. Bye bye. Actually, we'll do a share outro. So yeah, greetings and farewell.